Okay, so if you have three types of intermolecular forces, you can have van der Waals interactions, hydrogen bonding, and dipole-dipole interactions. In your notes you should, sorry you can hear my dog clicking, in the notes you should be able to see where I said that van der Waals interactions or dispersion forces are the weakest, dipole-dipole are the next, and then hydrogen bonding's the strongest. So if you have a molecule that can hydrogen bond, that would be the most important, being the strongest intermolecular force. If there's only dipole-dipole interactions, then that would be the strongest, and if it was only van der Waals interactions, that would be the strongest. Does that make sense? Good. Sorry if this is weird. I don't know if you can hear my dogs clicking in the background. I'm in my bedroom because they tend to be less vocal when we're up here. Yeah, sometimes dogs are just loud. Okay. So, Keely, it's going to be really hard to do just a brief rehashing on nomenclature because it's pretty involved. But, let's see. If you're looking at something, I can actually make this... Okay, try and make this big for you. Hopefully, let me check what that looks like real quick. Okay, that's better. Wait, what am I trying to find? I'm trying to find like a nice medium here. There's really not one. Okay. So let's say I have this molecule, and I'm just making random things at this point. 1, 2, 3, 4, 5, 6, 7. So if you're looking at this molecule I have on the screen, you can see that it has a handful of substituents on it. So substituents are carbon groups that are not part of the parent chain, okay? If it's something that has like an oxygen or a nitrogen, then that's considered a functional group, not a carbon substituent, okay? So if I'm looking at this molecule, I would have to go in the dog paw. Kirsten, real quick note, you are not required to know those yet. We didn't get to those yet. Okay, so Keely, back to this. So if you see these different carbon groups here, I'm going to highlight the parent chain here because hopefully you can see that it is 8 carbons long. So if I start down, let's see, 4, 5. 2, 3, 1, 2, 3, 4. Okay, so this substituent here would be an ethyl group because it's got 2 carbons in it. Does that make sense? This substituent here is a methyl group. This substituent over here is also a methyl group. Now, if I'm going to see if I can highlight and just color in the parent chain here. Give me a second. This may or may not work. Okay, that's not what I wanted at all. Okay. Anyway, so this long chain here is the parent chain, okay? So if I wanted to name the parent chain, I would have to call that an octane because it's got 8 carbons, starting at one end here, 1, 2, 3, 4, 5, 6, 7, 8, okay? So like I normally do in class, I usually just write, you know, a parent chain name. I already know that there's 2 methyl groups and 1 ethyl group, so I would have a something something dimethyl and an ethyl on my octane. So then I go through and I have to pick the numbering which is going to coincide with the substituents having the lowest possible number. So that would mean that this carbon over here would have to be carbon 1. What's going on? Well, probably because she's hungry. I bet he stole her food earlier. Onyx, stop eating his chubby dog food. Okay. Sorry about that. One dog is stealing another dog's food. Okay. So I have carbons 1 and carbon 8 there. And so that would mean I'd have a methyl group on carbon 3. I'd have a methyl group on carbon 4 and an ethyl group on carbon 5. So if I wanted to name this molecule, I would have to name it, let's see. Ethyl would come first because it's alphabetical, 3, 4. So 5 ethyl, 3, 4, oops, dimethyl octane. Does that make sense, Keely? Missed the 2 questions that Glenna asked. We had the same questions. Oh, so regarding intermolecular forces, I didn't type anything for that because it's pretty straightforward, but we have three types of intermolecular forces: hydrogen bonding, van der Waals interactions, and dipole-dipole interactions. In the notes, I talked about how hydrogen bonding is the strongest one. Dipole-dipole are the kind of one in the middle, and then the London dispersion or van der Waals interactions are really, really weak. And so if you have only van der Waals interactions, that would be the most powerful or most important one in that molecule. If you had, everything has van der Waals interactions, so if you had van der Waals interactions and hydrogen bonding, the van der Waals interactions are so minuscule in comparison to the hydrogen bonding that they're not really considered very important. Does that make sense, Dustin? And then, in regards to intermolecular forces, are we correct that we look for the most powerful besides the London on carbons and hydrogens? Yes. And there's no difference between p and pi orbitals? No, there is a difference. So in atomic orbitals, meaning you just have an atom by itself, you have, sorry, I just saw that question from Keely. You're talking about the one on the methane, Keely? The 3 on the dimethyl? It's because there's a methyl group on carbon 3. Okay, so the difference between a p and a pi orbital, if you have an atomic orbital, you have s orbitals, p orbitals, right? That's how we did the electron configuration, 1s1, 2s, right? The pi's and sigmas are for molecular bonding. So when you have hybridized orbitals that are bonding two atoms together, that's when you get sigma and pi orbitals. So s's and p's are on atomic orbitals, and kind of the same sort of thing on a molecular orbital would be a sigma and a pi. Can we do a practice problem on labeling which force would be most important? Okay, well, sure. So if you look, I'll do a couple of them, but so for example, on this 5-ethyl 3,4-dimethyl octane, there's no hydrogen bonding possible because there's no oxygens, nitrogens, or fluorines connected to a hydrogen. There's no dipole-dipole interactions because there's no bonds between an electronegative atom and a carbon or hydrogen. Okay, that's kind of what you would look for. So the most important force on this would be van der Waals interactions. That would be the only one. Okay. Now if I scroll down here and try and make us a new molecule real quick. So what is going on? I'm having ChemDraw issues. There we go. All right, so this would be cyclopentane, and I'm going to add on an oxygen. So I'm going to make this a little bit spread out the way I'm drawing it on purpose. So if you were to look at this molecule, okay, I don't need 2 hydrogens there, but there we go. Okay, so hopefully everybody can see this problem. What I would see here, and I'll go ahead and label this, is that over here, like the whole molecule is going to have van der Waals interactions, or London dispersion forces, or dispersion forces, whatever you want to call them. Okay. Those are very weak though, and so they're not particularly important in comparison to the other two. Now, if you look down here at the carbonyl, that ketone that's right there, this ketone would have the ability to do dipole-dipole interactions, if I can spell it. Okay, it's not going to hydrogen bond because there's no hydrogen on there to bond. Okay, you have to have a hydrogen somewhere to have a hydrogen bonding, and there's hydrogen bond donors and hydrogen bond acceptors. We didn't get into that detail in class. I'm just interested that you can point out something that would have one versus the other. This one over here is an oxygen connected to a hydrogen, and so that one's going to have hydrogen bonding. So this whole molecule has all 3 of the types of intermolecular forces that we discussed in class, but the most important one would be the hydrogen bonding, because that's going to be the strongest of the 3 that are there. And I know that that's the strongest just because hydrogen bonding is always stronger than the other 2. Does that make sense? And then let me... Okay, good. I like this. This is fun. There's about a 10-second delay. FYI, that's just the nature of streaming because it's having to shoot it from my computer to like YouTube to you. So if there's like a weird pause, I'm sorry if that happens. I think the texting coming up is pretty quick, but the actual video feed is not as quick. I wanted to see if there was a place I could put on to make sure you guys remember how to label finding the different partial charges. And I don't remember which little box that is. Whoops. I would have to find it, but so I'll go ahead and just label this real quick, and then Amanda, I'll get to your question. So this hydrogen here would have a partial positive charge on it because it's connected to an oxygen, and oxygen and hydrogen have a big difference in electronegativity. Then the oxygen would have a partial negative because it's the electronegative atom. There would also be a partial positive on the carbon that is right next to... I just realized that you guys might not be able to see me highlighting certain things. Try that again. So this hydrogen there would have a partial positive. That oxygen would have a partial negative. This carbon would have a partial positive. This oxygen would be a partial negative, and then the carbon attached to that would have a partial positive. And that's just because anything that's connected to an electronegative atom, the electronegative atom will have a partial negative, and the things connected to it will be partially positive. Okay. All right, so Amanda, for resonance structures, since the original molecule, how do you know which one's more stable? Okay, so sometimes there's not a difference, okay? If you have a molecule, and let me draw you an example here. So I'm just trying to like scroll down so I can keep everything on there in case people have questions. So let's say I have a molecule of benzene, okay? Now that does not have a charge on it, but it does have resonance structures, right? So for benzene, I can show the electrons moving around the ring to give, let's see, what would essentially be this molecule. There we go. Okay, so these essentially would be resonance structures of each other. No big deal. I'll put my resonance arrows there. Oh my goodness, what on earth have I just done? Try that again. This technology is really cool, but it is not perfect. It's supposed to be double-sided. There we go. Okay. So if I have something like this, these two are both equally as stable as each other. Neither one of those have a charge on it. Okay. That said, let's say I took and I had moved my electrons. Come on, Twinkie. You can jump there. That's okay. Twinkie barks very, very loudly when he's interested in doing something. I'm trying to keep him from doing that so you guys don't have to hear that. Let me goodness. It's so hard to just show a tiny little arrow. Anyway, so you can basically have a molecule, I'll try and make this easier, Amanda, I'm sorry. You can basically have a molecule if you had like a carboxylic acid, okay, that's been deprotonated. So you have like acetate ion instead of acetic acid. The two resonance structures you would draw for that would have the same stability because they both have the same charge, okay? Where you could get something that would have less stability is if you had something called separation of charge, where say you took two molecules or two atoms, you put one charge on one and then the other one gets a charge also. So you'd have like a plus and minus. We had an example like this on the board in class the other day, so it should be in your notes. So if you had those two molecules, or those two atoms, a positive and a negative, they cancel each other out, so the molecule would have the same overall charge still, but it would be less stable than the one that had no formal charges on any of the atoms. Does that make sense? Oh wait, want to see Twinkie? Twinkie, say hi. He has lipstick on his nose. Red's on the floor. He looks lazy. That's because Red is lazy. Then... Amanda, you can't see me? Is anyone else able to see me? Okay, so people are able to see my video feed then. Amanda, I don't know what's going on. That's weird. All right, everybody sees me. I got it, thanks. Amanda, I'm sorry you can't see me and you can only hear me. That's really strange. You didn't get to see the dogs. Okay. Then, let's see. Next one, Dustin. On exam 1, 2008, there's a problem asking you to draw the most stable conformation of methyl cyclohexane. The problem gives the structure already. Oh, most stable chair conformation. We didn't do chair conformations, so ignore that. We haven't done those. Would it not matter where you move the methyl group because it'd be... Yes, and that is true. So you could move a methyl group on cyclohexane to any carbon, but chair conformations are a structural aspect we're not covering in the brief class anymore. I stopped covering it after the first semester, so... Okay, patience. Can you please go over acid-base reactions and equilibrium, determining which molecule is most acidic using structures? Okay, so I'm kind of running out of room on my... Okay, so... Okay, determining which molecule. Alright, so let's say I have any kind of molecule. I'll make one called terbutanol. Okay? And I say, I'm going to add that to something. What do I want to add it to? Let's add it to... Onyx, that was nasty. Oh. To sulfuric acid. Doesn't want to do subscripts for some reason. Okay. So the first thing you have to ask is, could an acid-base reaction happen here? Okay. And the answer is, it depends on the pKa's. So go ahead and look to see if you have something that could be an acid and something that could be a base. Okay. Because if you have something that can be an acid and something that can be a base, you can have acid-base chemistry. So I'll say that, yes, that's the case. Because if I look up here, I have an alcohol, and the pKa's for alcohols are about 16 to 18, give or take. So not super strongly acidic, but they can act as an acid depending on the circumstance. If they're with a strong base, for example, they could act as that. And then I have sulfuric acid, which is also an acid indicated by the term sulfuric acid, and it has a pKa of less than 0 because it's a strong acid. That was on the list of strong acids, and we know that all strong acids have a pKa less than 0. That's how the math would work out if you were looking at it from a mathematical aspect, okay? So then the question is, okay, if I have these two molecules in a system, both of them in theory could act as an acid, but I have to figure out which one's the most acidic, right? So number 2, which would be the acid and which would be the base? Okay. Oh my gosh, I can't spell tonight. And so for that, you look at the pKa values, right? So a less than 0 pKa is a very strong acid. 16 to 18 is kind of a weak acid, not even a good weak acid. It's kind of a really midline acid like water would be. So if you're looking at these, you'd say, okay, the stronger acid would be the acid. And then the alcohol can be a base because it has electrons that can take a proton, okay? And so if I scroll back, what am I trying to do here? There we go. So if I scroll back up, and I think structurally, what would it look like if I had a reaction going on between these two molecules? Okay. So an acid is a proton donor, right? And a base is a proton acceptor. So if my sulfuric acid acts as my acid and my alcohol acts as my base, then I would have to have an OH2 plus on the other side because it gets protonated. And then I would also have plus kind of the remnants of the sulfate, so HSO4, 4 minus. Okay, so then the question is, and my this chem program can't really show the arrows the way that I've been doing them in class to talk about it this way, but move that over a little. But I've been talking about which way the equilibrium would favor. And so for that, you would say you want to favor the formation of the weaker acid in the solution. So for this one, I probably gave you a bad example. I'm sorry for that, but it's the same thing. So for this one, the pKa for a positively charged oxygen is less than 0. It's actually about -1. You don't need to know that detail. The one for sulfuric acid, I think, is like -7. So if I were to look at these, and I would say, which one, why can't I, there we go, which one would be the weaker acid favored? It would actually be the one over here on the right side of the equation. So I'm going to indicate this using kind of some weird arrows compared to what I've been doing. So that would be the way that would be favored. This would be the less favored direction. Does that make sense, patients? I'm not going to put a pKa for my hydrogen sulfate or the bisulfate. You don't need it for us to be able to see which one would be the acid and the base in this situation. Now, I can also go through and label these as my base, my acid, and then if I keep going, this would be my conjugate acid. Whoops. And then over here would be my conjugate base. So as long as you can identify the pKa values, and I wouldn't give you one on an exam where they would both be less than 0, where you'd have two strong acids. I always give you guys a weak acid and a strong acid if I do that, or two weak acids. So don't worry about that, but you should be able to look and say, okay, the weaker side is what gets favored, okay? So hopefully that makes sense. All right, so that was in my books. Keithley, I'm sorry. That's just everybody telling me. No, it's all squiggly. I don't know anything about computers, though. That's weird. Savage. I don't know why Anthony would be having trouble. Everybody else was able to get on, so... let's see, Dustin. Staggered and eclipse Newman projections. We did not cover those. Do not study anything we did not cover in class. I am not going to give you questions on anything that we covered in class. Same number. Exam number 5, drawing and labeling hybridization geometry was at tetrahedral. CH2, CH2... There's a typo in there somewhere. That's so sad. How about you not go bald in class? I'd appreciate that if you didn't pull all your hair out. I mean, if you shave your head, that's okay. But, so that, Dustin, I said at some point, I think, that there might be some typos in some of those. If you had CH2, CH2OH, you would have a carbon that doesn't have enough on it. Yeah, okay. So that was a typo then on mine, and I would have had to have fixed that. Sometimes I don't catch things like that. I'm a lot better about it now than I was a few years ago, but let's say I have this where I add in an extra hydrogen here. There we go. So if you had this molecule, the oxygen and the 2 carbons would both be tetrahedral. And then if the, put it here. Let's say that this was my, because this one would be a little bit trickier. So let's say the formula was CH2CHOH. Okay. So the carbon here would be sp2. This carbon would be sp2. This oxygen would be sp3 in tetrahedral because it actually has only single bonds, no double bonds to it. So hopefully that makes sense. The benefit of hybridizing is that we're more stable. We form stronger bonds when we hybridize our orbitals. Glenna. That's basically it. Stronger. And then the triple bonds are the strongest because of the extra S character. They're rounder, so there's more overlap. Like if you think about like big balloons overlapping, there's more overlap surface area if they have the rounder orbitals because they have like higher S character. So that's why the triple bonds are the strongest. Double bonds and single bonds are the weakest. That said, they're still really strong bonds, right? Carbon-carbon bonds in general are really strong. If I scroll down to 2. Scroll down to, I don't know what you're asking me to do, Patience, I'm sorry. Oh, you mean the number 2? Sorry. Number 2. I got it, Patience. Goodness gracious. Whoops. Trying to move stuff around. Keely, if you do poorly on this test, you have 400 points left, so you can do the math on that. If you got a 0 on this exam, the highest grade you would be able to get in the class would be an 80%. For my own sake. You guys are killing me. I'm sure you can probably say I'm killing you too. Here, have some Twinkie Cam. Hi, Twinkie. Twinkie Cam. Okay. Onyx, wanna come here? Is the exam going to be hard? No. Oh, you're dying. I like that. Can you do the 4 isomers of C4H9N? We could only get 3. Okay. So let me... Twinkie Cam. It's like if I lay in bed, they won't bother me. Trying to think of the easiest way to do this. Hold on. Let me open up. Give me just a second. I'm going to open up Paint. At least I'm going to try. There we go. Okay, so hopefully you can see I just switched over to the paint instead. Okay, I'm doing this one because I can actually use my finger on this, I think. Yeah, so that might be easier. So C4H9N. So how many units of unsaturation would we have on C4H9N? So 2n plus 2, so 8 plus 2 would be 10, right? That would be how many we would need if we had a saturated chain. We also have to factor in a nitrogen, which means we have to add 1. So that would mean for a saturated molecule, we would have 11. We actually only have 9, which means we're missing 2 hydrogens, which means we have, oh my gosh, what am I doing here? Which means we have 1 unit of unsaturation. OUO. UOU. Okay. So 1 unit of unsaturation. So let's do 4 with a nitrogen on it. And I'll put a double bond there. Then I'll do another one. But this time I'll put the nitrogen over here. And I'll keep the double bond there. Then, let's see, tools, erase. Oh gosh, can I not just like, oh, my goodness. Okay. What if I had nitrogen with a double bond? I could have, let's see, oh my. One, two, three, 4, 5. So, well, okay, I lost. Okay, Dustin, is that... Well, there's only 4 hydrogens, patients. C4H9. I don't know which one you guys are looking at, because David asked another one. But Dustin, can you see that there are lots of options here? I could have a chain of 3 carbons with a carbon coming off of it, like that, and a nitrogen coming off. So you can make branched chains with the nitrogens, you can make branched chains with the carbons. I could have a cyclopropane, which would be 1 unit of unsaturation, with like an NH2 group on it and a CH3 group on it. So there are lots and lots of options for units of, or isomers with that formula. Okay. 4 isomers of C5H10Br. Oh, that's because that one had a typo in it, so that would be pretty hard to do. So that one, if you want to try it again with C5, somebody asked me about that one the other day, and I was like, oh, that's because that one is not correct. Try that instead, and you should be able to get a lot of them. C5H11Br. I gave you something that you couldn't make unless you made radicals. The Organic for Dummies book's a pretty good book. I know Dr. Thompson keeps one in her office for people. Samsonite. Cyclo in the isomers. Ah, yeah, don't forget to count cyclic rings. Always count a ring as one. If you have 2 rings, it counts as 2. So if I had something like this, 2 fused rings next to each other, that's actually 2 units of unsaturation. Okay. Yeah, if you still tried to do C5H10Br, you'd still be minus a hydrogen somewhere. It wouldn't come off right. I think I've gotten everybody's questions so far. I've read down to Keely's It's Been Helping. If you have one up there somewhere that I got lost on, please resubmit or, you know, ask it again. Oh man, what if this makes me YouTube famous and people start recognizing me at, like, Wendy's? Like, hey, aren't you that lady on YouTube? I need to get, like, YouTube eyebrows to do that. Thank you, Glenna. I appreciate you laughing. Totally on fleek. A p orbital and a pi orbital? Yeah. So remember when you're doing electron configurations, you have like 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, etc., right? Those are s's and p's. There's also d's and f's, okay? If you have d block, the transition metals, and then the f are the ones down in the lanthanides and actinides. Thanks, Glenna. And you're welcome, Carrie. So, a pi orbital is the doubles and triple bonds that you get when you're in a molecular orbital. So the difference between a p orbital and a pi orbital is a p orbital is an atomic orbital, meaning it's just what an atom naturally has, and then a pi orbital and sigma orbitals are molecular orbitals that you have when you are actually looking at a molecule with hybridized orbitals and stuff binding to each other. Does that make sense? It's easy to get them confused, though, because they sound kind of the same, and they're very similar, right? So, like, p orbitals give rise to pi orbitals, so it makes sense that they're kind of confusing, but I do think it's an important distinction to make. Oh my gosh, he's so lazy right now. If I say his name, he'll look up at me, but let me... Oh, look at his dog. He's like oozing off the table. Dogs are ridiculous. Oh, hi, Pinky. I wasn't talking about you on TV. My dogs are ridiculous. I also bring them in on study day, so you guys can come and love on dogs if you want. I know some people are in you know, dorms and stuff, and you don't get to pet on puppies enough as you would like. Glenna, focus. You have an exam tomorrow. You know, sometimes the aha moment does happen, and it'll kick in, and I'll actually watch it happen in class. Anthony had one the other day, if you remember, and my other class had one the other day. It's just really funny. You're scared of dogs? Even, I mean, like, how can you, seriously, how can you be scared of that? Look, they're like so lazy. My dogs are stupid. You can also see my hat rack. Yes, I have a hat rack. I'm the same way, Glenna. And if I'm away from home, like if I'm traveling or something, I don't have my dogs, and I see somebody walking a dog, I almost start crying. I get like, oh, I miss my puppies. It's so stupid. Well, Keely, not everything comes easy to everyone. If we were, we would all be good at everything. It's okay. We just gotta get you through the class. So when you want us to hybridize, do you want each bond labeled? If I ask to label the hybridized bonds, then yes. I will specifically ask for that, though. Or I could say label the geometry, or, you know, circle sp3 hybridized atoms, you know, stuff like that. Cyclohexane. Ah, that's a good one, Glenna. Here, let me pull back my, I need my drawing one again. Whoop, there we go. This is so cool. I'm sorry, I'm fangirling over this technology, because this is a lot better than it was a few years ago when I tried to do it. Okay. Cyclohexane 126 trial. Okay. Let's draw that. I was really proud of myself the day I came up with that question. So, put one there, 3, 4, 5, 6. So if I asked you to name that, would you name that cyclohexane 126 trial, or would you name it cyclohexane 123 trial? Because you want it to have the lowest possible numbers, right? That's right, David. There are a few exceptions, but those are the things that I said we're not learning about in this class. So, because we do things briefly. I say that all the time. You guys are probably tired of me saying that, but here, hold on. Oh, come on. Why can't I? Here we go. There you go. Nice. Okay, cyclohexane 123 trial. If you call that cyclohexane 123 trial, that's a slight, I've basically told you guys just to always leave off the E's. So I would count that as correct, but if you saw this and it said cyclohexane, that's technically the correct way, because you don't want an E next to it, or and basically two consonants next to each other. It's like how we call things monooxygen, we call them monoxygen. Brief means you get to the most important stuff, so brief is good. I agree. So how long am I going to be on here? I was going to get off at 8, so 15 more minutes-ish. Does it go with the prefix or suffix? Dustin, any of the halogens go as a prefix. And if you ever encounter something that is like methylene chloride, that's an old name. So there are some names that are kind of ingrained. Okay, yeah. There are some that are kind of ingrained that are, you know, old names like acetone, stuff like that, that's not technically correct. Methylene chloride's pretty much the only one I can think of that is halogenated that we have kind of a misleading common name for, though. If I have a 1-methyl-3, I know the 1 is the carbon it's located on, the methyl is the number of carbons. Keely, I don't know what you're talking about. 1-methyl-3 what? Like 1-methyl-3 isn't a complete name, so I'm not exactly sure what you're asking me. If you had another 3, though, that would have to be the third carbon would have to have another substituent on it. That's right, patience. We just don't count the dies and the tries. So, and you can use this this program that I'm using to check your names too. So if I put on something like that, and then okay. So let me go through and name this molecule, but let's put on, let me see. I wanted to make some of these iodines. Okay. So if I wanted to go through and name this, I'll highlight it, circle it, and I don't think, let me check real quick. On my feed, I don't think you can see when I have the drop down. No, okay. But there's basically above the structure and draw thing at the top, there's one that says tools, and I don't think you guys see that when I clean it, but, or when I pick it, but underneath that it says generate, and then you pick name for structure. So this would be 4,4-diiodo-3-methylheptane. Okay, so the, oh, you know what? That's because I was trying to do an E for patience. Let me change that. Okay. I thought I had it all. Apparently I did not. There we go. So you can see that the ethyl comes before the iodine, even though D comes before E. Okay. Yeah, it is a program that takes a lot of practice. I mean, that's, I actually have a little, like, I don't want to call it a tutorial, but it is like a little thing on how to make structures in it at least, so if you guys wanted it. Okay, so I have 3-ethyl, Keely. That means that on carbon 3, there is an ethyl group coming off. Then it has 4,4-diiodo. That means on carbons 4 and 4, meaning the same carbon, there's 2 iodines, and that the heptane's a parent chain. So if my iodines were not on the same carbon, let me delete one of those and I'll show you what it would do. It would change the number that it's on, but I would still have an iodine if I put it somewhere. So So if I took this and came up with, oops, there we go. Tools, generate infrastructure. So now you see it says 2,4-diiodoheptane because now the iodines are at carbons 2 and 4. So all the numbers are just representing the placement on the parent chain. All numbers will represent placement, like which carbon something's on. I'm gonna check real quick to see if anybody emailed any other questions in. I don't think. No. Okay. So if you ask the ChemSketch people, they say that ChemSketch is compatible with Macs, but you have to download something with it, to some sort of like simulator or something, to basically make the program think it's running on a PC. But other than that, not really, that would be free. And to be honest, I don't think it would be worth your all's time to pay several $100s for other software. Oh, inductive effects. So inductive effects are when you have an electronegative atom kind of downwind of a molecule or other atoms around a molecule. The inductive effects are basically going to make something able to be more acidic because it will help with stabilizing negative charges. So if you look up, let's see, let me show you a good example of inductive effects. Okay, so this is acetic acid. If I do the Google searching for the acetic acid pKa, 4.76. So I said 2 to 4, that one happens to be 4.76. So now if I type in a related molecule, which is called trifluoroacetic acid, where instead of having 3 hydrogens attached to my carbon, I would have 3 fluorine. If you did that, and you look up the pKa for the trifluoroacetic acid, its pKa is right around 0. I've seen it as high as like 1, so I'll keep that here just so we can keep consistent with the less than 0 being strong acids only. But yeah, so you can look here and see the difference in these is only fluorines versus hydrogens, right? Hold on. Oh, that's me, I'm sorry. So the difference between these two molecules, because they have the same amount of resonance, they have the same size of atoms, they have all that. The difference is that there are these 3 really electronegative atoms downwind of the hydrogen that would come off, meaning when you deprotonate the acid, it's going to stabilize that negative charge by drawing the electron density into the molecule. It's a really hard concept to understand, to be honest. Aw, you guys are helping each other. Oh, good Lord. I'm just reading. I didn't have the chat box up when I was explaining that. What the hell is an inductive effect? That would have been really scary. Okay, one more question. I need to go get something to drink. I'm getting thirsty. And I have to write an exam for you guys still. One methyl ethyl as an isopropyl. Keely, we didn't do isopropyls, so I wouldn't ask you to do isopropyls. Isopropyl just means it's a propyl group connected in the middle, instead of at the end. So it's a middle carbon instead of the ends, but we haven't gotten to those. Some semesters I cover them and some I don't. Words are hard. That was an easy question, though. So I'll take one more. Okay. It sounds like you guys got all your main questions out, so I'll go ahead and hop off for tonight. I'll write y'all's exam. It'll be 4 pages, one side each page. Thanks for everybody for signing on. This was a lot of fun. This is pretty cool technology. Diol means 2 alcohols. Dimethyl's 2 methyls. Diol's 2 alcohols. Dioic acid would be 2 carboxylic acids. All right. Good night.